This is a word problem, a variant of the word problem that I told you that goes all the way back to Kleene. The attack will succeed only if the enemy is taken by surprise and the position is weakly defended. The enemy will not be taken by surprise unless he is overconfident. The enemy will not be overconfident if the position is weakly defended. Therefore, the attack will not succeed. And it turns out this is a valid argument, although we'll make absolutely certain by trying to do a resolution for you. So the variables are the attack will succeed is S. The attack will succeed is A. The enemy is taken by surprise is S. And position is weakly defended W. And the enemy will not be taken by surprise unless overconfident is C. Those are enough variables to formalize it all. Translating this becomes A implies the conjunction of S and W. If the enemy is taken by surprise, then he is overconfident. If the position is weakly defended, then the enemy will not be overconfident. And the conclusion is therefore, the attack will not succeed. Before you get to the proof, what you have to turn it into is a refutation situation. You see, originally we want to know whether this is a logical consequence of these. Well, to say that not A is a logical consequence of these is to say that these and its negation are inconsistent. So we negate this, we get very literal-minded, not A. So the question then becomes, here the question was, does this follow? Instead, the question is it consistent with all the others? So a validity question can always be reduced to a consistency question, and many proof systems work that way. Not all, but many proof systems work that way. And then the next step is to convert these into clauses. Remember, clauses are implications in which only variables are involved. So not A, well, it's the same as A, and we can turn A into a clause just by making it on the right-hand side of an arrow. So this formula is logically equivalent to this clause. This isn't a clause because there's a negation in it. This is very important. Clauses don't have any other connectives in it. There's just a clause is just some variables and one single implication. If you don't reduce the things to clauses, your results may be meaningless. Already a clause. This is not a clause because it has a negation in it. But there's a really easy way of dealing with negation I mentioned before, is what you can do if you have not C on the right-hand side of the implication, you just remove the negation and move the C over to the left-hand side. So this is logically equivalent to WC implies, and that is a clause. And then there's this one here, and this one is also not a clause because there's a conjunction in there. And furthermore, this is not equivalent to this is not even equivalent to a single clause, because what it's saying is that A implies two things. But, and this is hardly magic, it is equivalent to two clauses, and these are just two clauses that say, one says that A implies this, the other says that A implies W. So the question now is, are these clauses consistent? well, or inconsistent, we can ask either question. Okay, so these are the clauses, and we want to know, and we want to know, there's 5 of them, and the question is, are they consistent? Now, resolution is not, I don't recommend it for manual proofs. It's not the way people like to prove things. So, for example, it's not obvious looking at these whether they're inconsistent. We are able to look at the original natural language one and get an idea that it's a valid argument. It's not obvious these clauses are consistent or not. So here's what we do. The way the resolution proceeds is we apply the resolution rule and generate more clauses, hopefully simpler ones, and our goal is to generate the empty clause. Because if we can generate the empty clause is false. So what we've shown is that false is a logical consequence of these, which is to say they're inconsistent. So that's what we try to do, try to generate the empty clause. Now the resolution rule, it's extremely simple. That doesn't help people much because it's confusing, but it's great for machines because there's just really very little to do. And what you do is you look at pairs of clauses in which a variable appears on one side in one of the clauses and on the other side in the other. So there's, for example, there's this pair here. So we can put them together. And C appears here and C appears here. So the C goes, but we just merge the remaining parts. So this becomes so we put these two together, and that produces and we can put these two together, and we're going to get then we put these two together. So here the S is on one side and the other, so the S cancels and all we get is this. And then we're done because we put these two together and we get the empty clause. So that's a resolution proof, not a very difficult one. Now let's backtrack. We were able to use the resolution rule to derive the empty clause, which is 0 or a contradiction. That means, since the resolution rule is sound, anything you derive using it is a logical consequence of the two rules that were combined. What that means is these original ones were inconsistent because you can derive an inconsistency from them. There they are again. This means these original formulas here are inconsistent. And finally, what that means is that not A follows from 303. So what we've done is we've shown the argument to be valid. Okay.
So you can use a clause twice?
Oh yeah, and generally you will. It's very important when you derive, in resolution, when you derive a new clause from an old pair, it's very important not to throw the old ones away. Because the new one is not equivalent to the conjunction of the old ones. The new one follows from the old ones, but it actually says less because this, for example, this doesn't say anything about C, whereas these two did say something about C, and therefore you can't throw away the old ones. With resolution, you're just increasing the clauses you have. And sometimes we didn't follow any dead ends. We could have followed some dead ends. We might have, for example, combined these two, and that would have given us another clause which really wasn't useful. So you can't, it's like, well, it literally is a search. I'll show, that's one thing I'll show. But there's no harm done in generating more clauses than it needs. Okay?